here and the former coming.
Sure.
I don't think this is working. How to this one? Yeah, it's not working. It seems.
It's not working.
Yeah.
It has a green light, so that should
The
work.
green means it works, right?
Yeah.
Okay. No worries.
No sound, maybe.
To capture
Oh yeah. Oh, I see. I see. I see. I see.
for the video, the microphone for the microphone.
Okay.
Oh, okay. Okay. Thank you. Oh, yeah.
All right, let's get started. Good afternoon, everybody. My name is Alex Abrenidis. I'm very happy to welcome you to our first department colloquium for 2024-2025 academic year. And we have an innovation this year where we also have food, so hopefully that works well with everybody and we have more people to come in. With that, I'm going to just pass it on to Dr. Longfei Sangwan. Hopefully it's not too far from the real name, but I'll try. Who's going to introduce our speaker?
Sure. So, yeah, good afternoon. I'm Longfei. I'm assistant professor at our computer science department. So today is our first, seminar throughout this, semester. So I would like to introduce the speaker, Yu Ze. So Yu Ze is currently a postdoc working at Carnegie Mellon with Peter and Srini,
Yeah.
networking stuff. So Yu Ze got her PhD in Hong Kong, Chinese
in Hong Kong,
right?
yeah.
So last year. So she did many amazing work in mobile computing and embedded systems. Publishing works in Movicom, in Census, and got many awards such as Movicom Best Paper Award, and I think ECS Writing Star Award this year, and also fellowship. I mean, a bunch of stuff. I will not mention, and everything here. So yeah, so today she's gonna give us a talk on her PhD thesis stuff, right?
Yeah.
Autonomous driving from perception to HD mapping. So without further ado, it's your stage.
Okay. Okay, thank Professor Shangguan for the introduction and for the invitation. Okay.
Yeah.
Yeah, hello everyone. I'm Yu Ze He. I'm currently a postdoc at Carnegie Mellon, and today I'm excited to share with you my research on infrastructure-assisted autonomous driving. So we all know that autonomous driving is the future and has the potential of revolutionizing transportation, mobility, and safety. However, in recent years, we've seen a lot of traffic accidents involving autonomous vehicles, which has raised a lot of concerns about the safety of autonomous driving systems. An important reason is that each autonomous vehicle operates independently, solely relying on the data from its own sensors, and this makes the system's reliability quite limited. For instance, many accidents are caused by the limited field of view of onboard sensors. These sensors can be occluded by surrounding objects, which can create blind spots. Also, sometimes vehicles can fail to localize themselves accurately, leading to misjudgment in their distance from other vehicles or pedestrians, and consequently resulting in accidents. So in response, an emerging paradigm is to leverage smart roadside infrastructure to assist autonomous vehicles. For example, smart lampposts are equipped with sensors and computing units. These sensors are usually installed at a high position, which means they get a wider field of view with almost no occlusions. This data can be transmitted to vehicles to improve driving reliability and safety. So my research focused on designing infrastructure-assisted autonomous driving systems, and I have designed and implemented several vehicle infrastructure cooperative systems on perception, localization, and mapping. They all have been tested in real-world scenarios. In this talk, I will present three works, VII, AutoMatch, and VI Map. So my first work in this area is VII, and our idea is very straightforward. We aim to align the 3D point clouds from the vehicle and the infrastructure. In other words, the point clouds from the infrastructure should be aligned with the vehicle's coordinate system, which is referred to the problem of vehicle infrastructure point cloud registration. And why we want to do this? Here we use a motivating case study to illustrate the purpose. Here is a motivating case study. We can see two LiDARs are mounted on the infrastructure and the vehicle respectively. And this is a picture of our smart lamppost test bed deployed on our campus. Below are the vehicle point clouds and the infrastructure point clouds. Here we show the point cloud registration results in the bird eye view. The infrastructure point cloud is pink and the vehicle point cloud is green. We can see that after aligning the two point clouds, the effective sensing range of the vehicle can be extended from about 38 meters to around 65 meters. And on-vehicle perception tasks, such as object detection, can thus benefit from the extended sensing range. Moreover, we can see that the density of the point cloud is also increased. So the vehicle can detect the objects more easily. Formally, vehicle infrastructure point cloud registration problem can be defined as follows. Given the infrastructure point cloud and the vehicle point cloud, we want to find a transformation T that consists of a rotation matrix R and a translation vector T. And this transformation will be used to align the two point clouds. Although with so many benefits, this problem presents several major challenges. First, each point cloud frame contains massive points and needs to be processed in real time. Second, there exists a large perspective gap between the vehicle point cloud and the infrastructure point cloud. And the overlap between them is not only small, but also varies dynamically as the vehicle moves. So to address the aforementioned challenges, we propose VII, and our core idea is to only focus on several carefully selected semantic objects, and to extract saliency points from these objects. Then, by matching these saliency points, we can finally register the vehicle and infrastructure point clouds.
So what's the meaning? What's the meaning of these silence points here?
Yeah, it's more like key points. Yeah, okay. It's key just point. We want to find a a nice
Gotcha.
So the pipeline is. I'm sorry. The pipeline is as follows. We first perform semantic segmentation for both infrastructure point cloud and vehicle point cloud. And then we only focus on several objects in it. For example, the traffic signs, the lane lines, the curbs, and the road. And then we extract the saliency points from these semantic objects and only extract the vertices and center of these objects to serve as the saliency points. And finally, we want to match these saliency points so that we could find the transformation T based on the corresponding saliency points. So next I will introduce each module separately. We first segment point clouds into instances with semantic labels. and only extract 4 categories of semantic objects, including traffic signs, lane lines, curbs, and road. And these objects are most static, distinctive, and common objects in traffic scenarios, thus are robust to dynamic scenarios and can be easily recognized. Then instances with regular shapes, such as traffic signs and lane lines, are used to extract the saliency points. We propose a novel algorithm here to extract the saliency points for each semantic instance. The pipeline is as follows. We first estimate the plane of semantic object and filter points that do not belong to the object. Then we project the 3D point cloud to 2D point cloud, which will be further splatted into a binary image. Finally, we leverage the prior that our selected semantic objects usually have regular geometries. So we feed the binary image into these geometry primitives. And by extracting the vertices and the center of these primitives, we can finally find the semantic saliency points. And finally, we project these saliency points back to 3D. So now we get all the saliency points. But before we're using these saliency points for registration, we want to explore more about the point cloud in traffic scenarios. And luckily, we found that a nice property here is that ground is a unique and strong prior in traffic scenarios. And by exploiting the ground, we can obtain an estimate of the rotation matrix between the vehicle and infrastructure point cloud pairs. Specifically, we use ground-related semantic objects, such as curbs and road, to estimate the normal vector and the direction vector of the road. And by aligning these two vectors, we can get a rotation matrix, RG, which serves as a registration prior and will be used for speed up the registration process. So the registration module, it takes the saliency points in both ends as well as the rotation matrix RG and estimates the final transformation. Here we adopt the framework of roadside algorithm to do the registration. And here we propose 2 heuristics to greatly accelerate the classic roadside algorithm. First, each saliency point has 2 labels. Recall that each point has a semantic label and a primitive label. So when picking saliency point pairs, we only match 2 saliency points that have the same 2 labels, which will narrow the searching space of corresponding saliency point pairs. And second, we quickly check whether an estimation is a valid one by comparing the similarity between our estimated estimated rotation matrix R and the registration prior RG. And if the similarity is low, we terminate the iteration early to reduce the computation. And for the system evaluation part, we collect the first multi-view LiDAR point cloud dataset that contains both the vehicle's view and the infrastructure's view. The first dataset is collected on an indoor autonomous driving test bed, and the second dataset is collected using the smart lamppost test bed. In total, we collected around 900 point cloud pairs, covering 3 rows with a total length of 1.12 kilometers. We first evaluate the application level perception improvement. We use 2 metrics to evaluate the application level results. The first is effective sensing distance. It reflects how far a vehicle can see. And the second is point cloud density. It reflects how clear a vehicle can see. The left figure shows that our approach almost doubles the vehicle's sensing range, and the right figure shows that VII significantly improves the point cloud density, which is even higher than the density of the expensive LiDAR used in the public KT datasite. Next, we want to evaluate the performance of our system with other point cloud registration algorithms. We divide each of the datasets into two groups, an easy group and a hard group. We compare with 4 baselines, ICP, NDT, ACIA, and FGR. We adopt the matrix relative rotation error, relative translational error to estimate the registration accuracy. And here the RRE and RTE measures the registration errors between the estimated transformation and the ground truth transformation. Besides, we define a registration as a success when the RTE is below a threshold, so we have a matrix of success rate. Here we show the results on the real-world test datasite. This table shows that the average rotation error, translational error, the runtime, and the success rate. We can see that our approach achieves higher success rate and delivers a 5 times improvement in accuracy and 2 times speed up over other baselines.
Question. So I know your algorithm can sort of like run very fast in terms of the registration, right? But my understanding is like your roadside infrastructure have to send this large amount of data, right, to the car. This can cause some
communication delay.
How to deal with this issue? Or?
Okay. So for the first is we do not have to transmit raw point cloud, because when we have the silency points in both ends, we use these silency points to do the registration and get a transformation between them. And using this transformation, we can actually, transmitting any kinds of information. For example, we can transmitting the bounding boxes from the infrastructure to the vehicle, but we still use this kind of transformation. And the work is mainly about how we can accurately get the transformation between these two coordinate systems. And in the challenge of they have very distinct perspective. This is
essentially you don't have to
in our
transmit all the data.
But in our paper we show the benefits of such transformation, such registration using the raw point clouds. And this is also the comments from reviewers. They are saying, you are transmitting the raw point clouds, and there will be a lot of communication delay. Of course, we also have papers, other works that address this. For example, we have VIPs, which transmitting the bounding boxes between the infrastructure and the vehicle. Maybe.
To answer that question, I was also thinking about the vehicle density, because if you have a lot of vehicles, you have 2 options. Either build an algorithm that is resilient to failures of communication, or you're going to increase a lot the retransmission rate. Is this a problem? If you have a lot of vehicles and a lot of stations?
If we have a lot of vehicles, actually this algorithm is between 1 vehicle and 1 roadside infrastructure. And if we have a lot of vehicles, these vehicles will do their own silency point extraction independently, right? And the roadside infrastructure, it can transmit its silency points to all the vehicles, and the vehicles can do this kind of registration process on its own. So it's more like a scalable fashion, I think.
So if a message fails, just fails. That's fine.
And I think the goal of infrastructure-assisted autonomous driving is to provide the vehicle with more information. But without this information, the vehicle can, drive by its own. Maybe.
piggybacking a little bit on that, so I understand the scalability from the computation point of view and from the communication, let's say, but if you have a lot of vehicles, wouldn't that mean also that the images that the infrastructure takes are blurred to some degree, that they're not, they are unknown because there are vehicles driving, and best case scenario, part of the ground is
occluded.
Yeah, it's not
Yeah.
visible.
Yeah, this is something I think is unavoidable, but if we have to have a solution, I think one property of infrastructure is that it stands there and it, observes the road section at a standstill. So when there are no vehicles and we are selecting objects that are static, right? And when there are no vehicles, the infrastructure can actually extract these saliency points, at any time. And these saliency points tends to be, last forever, or at least last for a period of time, And from the infrastructure's perspective, it can have these saliency points at a very, accurate way. And for the vehicle's perspective, you are right. If we have lots of vehicles and they may occlude each other, and each vehicle may do not have, enough saliency points to do the registration, and that's a problem,
But from the infrastructure point of view, basically you don't really need the live camera because the road is going to be the same. They change the lines, but the road is basically the same. So even if at that time there's a lot of congestion, let's say, there was a period of time where there was not, the infrastructure has a good picture. The cars may not have a good picture.
And I also want to mention that to do the point cloud registration, actually we only need 3 very accurate points. For example, if for the 2 point clouds, we only need 3 pairs of points to do the accurate registration. So as long as the vehicle can, accurately detect 3, it will be good, Okay, that's basically the end of, no end, okay. We also show the performance of our key module, which is the saliency point extractor module. Here we compare our saliency point extractor with 3 widely used key point extraction algorithms, Harry 3D, ISS 3D, and SIFT 3D. We visualize the key points extracted by the 3 baselines and our saliency point extractor in this figure. We can see that the key points extracted by the baselines are scattered randomly in the space, while the key points extracted by our algorithm is highly interpretable. They are all geometric vertices or centers of the semantic objects. And here are some real-world visualization results. From the first figure, we can show that VII can actually align the vehicle and infrastructure point cloud very accurately. So the takeaway is VII aligns vehicle infrastructure point cloud pairs to extend vehicles' sensing range and improve point cloud density. And VII achieves centimeter accuracy and real-time registration by extracting and aligning very few saliency points from the semantic objects. So this is my first work, and although this work, it shows a promising way of leveraging infrastructure to assist vehicles' 3D perception, it requires deploying the expensive LiDAR on the infrastructure, which may not be available in the near future. So in the second work, we explore the possibility of using existing infrastructures to assist autonomous vehicle. And here comes our work entitled AutoMatch.
I have a question about previous projects.
Okay.
One thing is if I drive my vehicle close to the station, so the first time I need to communicate with you to exchange over point cloud, right? And I will get the transformation metrics from you, right? So one thing, do we need to do this, repeat this for every frame?
Oh yeah, Okay, you can have two options, which is not included in this paper, but I think there are two options. The first is you can do it every time, every frame, and the second or the smarter way is you can use your vehicle's own localization devices such as GPS and IMU to, for example, if at frame T you have the transformation, right, and in the following frames you can use your IMU to calculate your own transformation, for example, your own movement, and by adding your vehicle's own movement with the original transformation at frame T, you can get a transformation at frame T plus X, for example.
I'm thinking about if I'm moving, right, even I can get update the transformation metrics based on my direction, my speed. I still need to get new point data from cloud data from you, right? Because I don't know what happened in front of me, maybe 5 cars, right? So.
Oh, I think in the if we are talking about the information you get from the infrastructure, I think is it's not very urgent or.
I think that if I don't get new data from you, I use the old transformation metrics and I update locally. I don't know what's happening because I don't get any data, any update from you. If I communicate it with you, just like syntactic density, communication okay, but also I see the latency. For example, if I have several vehicles communicating together or edge device, this edge device is powerful enough to handle these several computations at the same time.
Okay, first, the infrastructure communicates with the vehicles in a broadcast way. For example, it can broadcast information to all the vehicles, right? And all the vehicles, it can do its own computation, and whether it can handle this, and I think it depends on the communication capability of your own device, right? And you can choose not to use the infrastructure. And for the information update part, the infrastructure, it can sense to or broadcast the information of its field of view in not that frequent way, because once you have the transformation, you get the sense of your transformation between you and the infrastructure, and if we have this kind of bridge, then you can get the knowledge from infrastructure in any frequency. It also depends on how dynamic the thing is, right? And which is, I think, is beyond the discussion of this paper. It's more about how you strategically to update the information to all vehicles. Yeah.
I have a question. How that the LiDAR you use is degrees less than 180. If we use a 360-degree LiDAR, will it cover?
Do I need to?
Sorry, just 1 second. The person who's online cannot see the presentation and cannot hear you.
Oh, okay.
I don't know if... are you on?
Oh, I'm sorry.
Share the screen?
Yeah, I didn't share the screen.
Oh.
Oh, host.
Yeah, that's a problem.
Oh, who's the host?
Don't know, but okay, so
Forget it?
forget it. But what about mute? Are you muted?
Yeah.
Can you unmute?
Yeah, if I unmute the room. Yeah.
Then there's the problem. Okay.
Oh.
We'll deal with that later.
Okay. We could flip the screen.
We'll deal with
Want to flip the screen?
We'll deal with it later.
Okay.
No, so just share your screen, yeah.
Yeah.
Oh, okay.
Sorry. Now you can ask your question again. Sorry about that.
Oh, yeah. So I'm thinking that because I think vehicles now they are using 360-degree LiDAR. Use that to generate a point cloud. Then the point cloud that is in front of your vehicle and behind your vehicle, they are very similar. If there's no other like visual point on that road. So how do you make sure that the rotation map is now mirror or is correctly generated?
I don't quite get your question, but I think it's probably about how to decide the direction of the infrastructure's point cloud, right? And if it is your question, I think, as we mentioned, the road has its direction and the vehicle knows its driving direction. So when it gets the infrastructure's information, it can get an idea of the relative location between them. So the direction is not a problem, maybe.
Okay, so I understand this as the infrastructure broadcasting information to autonomous vehicles, and the vehicle aggregates its perception with the infrastructure's perception. Okay. So my question is more from a security and privacy perspective, because there are currently studies, very concrete studies that shows you can attack those kind of autonomous driving and perceptions. Not only from a system, not only from a software, but actually hardware. You can design patterns and you can 3D print surfaces to
I know what you mean.
LiDAR perception. So from this, now when I attack the infrastructure, I place an object that is specifically designed to obscure its perception. Wouldn't that mean it just creates a more vulnerability and risk for the vehicles? So is there a trust, and is there a trust mechanism in this whole system?
Okay, the security of this kind of infrastructure vehicle cooperation fashion, it do be a separate research problem or separate research area, and there are, like you said, there are works that can modify the point clouds or modify the image transmitted. And I admit this is a problem, but maybe it's not included in our discussion here, and it may belongs to another track of or another area of research.
When you just aggregate this information, it's not only a trust issue, it's also an accuracy issue. Yes.
Okay, so let's continue. So in the second work, we explore the possibility of using existing infrastructures to assist vehicles driving. And here comes our work, AutoMatch. And when we are saying we want to find existing infrastructures, actually we do find that traffic cameras, they present a promising opportunity. First, many traffic cameras, they are already installed around the intersections to monitor the traffic conditions. And also, it is worth noting that more than half of the serious accidents are occurred at the intersections. And the traffic cameras, it also have some advantages. First, they are usually installed at a high position, which makes their field of view much broader. And the second is the traffic cameras are typically fixed in place, so which makes them possible to aid vehicle localization. So in this work, we study the problem of leveraging existing traffic cameras to assist vehicles localization. Here shows an HD map and a traffic camera image. The HD map is highly accurate, and each pixel in it corresponds to a precise world position. So if we can find the pixel-to-pixel correspondence between the traffic camera image and the HD map, we could derive the 3D world position for every pixel in the traffic camera image. As a result, we can easily know a vehicle's world position if the vehicle is in the traffic camera's field of view.
Where does the HD map come from?
The HD map can be constructed by the drones, and there is like commercial softwares for the drones to scan the intersection and generating such high definition 2D high definition map. Yeah. I'm sorry. Why can I control this? Oh, okay. So to realize this, a key technology that is needed is called image registration. So image registration tries to match two images pixel by pixel so that the information in one image, for example, the world location information, can be transmitted to the other image. Formally, we want to find the transformation between these two image coordinate systems. And however, in our problem, we can see that the HD map and the traffic camera image, they are very different in both perspective and scale. And our idea is similar to our first work, which is to focus on the ground signs here, because they are printed at every intersection and they are distinctive structures that can be used for matching different images at a very high accuracy. For example, look at these two images. If we can match the ground signs, the two images match perfectly. As a result, each pixel in one image is correctly paired with itself in the other image. Although this idea at high level is very straightforward, we need to address several challenges before it can be applied in real-world settings. And like the first work, we also want to extract these key points from ground signs. For example, like these red points, and they are anchors that are actually needed to do the image registration. However, in reality, we can see that this is not as easy as the example we showed before, because there are many imperfections in real-world settings, and these imperfections can make the key points very difficult to detect, as shown by the yellow points. The detected yellow points are messy and mix the key and non-key points. So there is, so how we solve this problem? Actually, we found there is a very similar problem that has been extensively studied, which is the facial landmark detection. Yeah, basically, facial landmark detection, it aims to detect structured facial landmarks, such as our eye corners. So similar in our problem, the facial images also have many imperfections like uneven lightings and occlusions by hair and etc. So how does facial landmark detection do to address the challenges? Actually, the key idea of these methods is to learn this facial landmark template. So can we apply the similar idea of facial landmark template to our ground signs? And actually we can, but there are two major issues. First, unlike all human faces, we all have like two eyes and one nose, right? But there are different categories of ground signs, and each category of ground sign it actually have very different landmark template. And if we want to use this template, we need to train a lot of detectors based on different templates, different categories of the ground signs, and which have a very high overhead. So our idea is to design a novel unified landmark template applicable to all categories of ground signs. And if we apply this idea to detecting the landmarks of the ground signs, we can find that although the landmarks have rich structure information, they can cause a lot of errors in positioning. For example, there can be like several pixels of error in the key point location. So how do we solve this problem? actually we found that another kind of detector, which is called the corner-like key point detector, it can locate ground sign key points accurately, but together with many outliers. So our idea is to integrate the two kinds of detectors to have the best of both detectors, the robustness from the landmark detector and the pixel level key point localization accuracy from the corner-like detector. So how to integrate these two detectors? We design a new method. The inputs are the landmarks and the key point heat map. In the heat map, brighter pixels represent more corner-like key points. And the key idea here is the landmarks helps us to locate the approximate locations of key points. And then we use corner point heat map to fine-tune the positions of landmarks. As a result, the final key points are both structurally and positionally accurate. So let's put everything together. AutoMatch first detect the ground signs in both images. Then we use our proposed landmark key point extractor to extract key points. And the same operation are done for the other HD map image. Lastly, we match the ground sign key points and estimate the transformation based on the key point correspondence. So to evaluate AutoMatch, we collect a new dataset which includes the traffic camera images and HD maps at intersections. In total, the two datasets contains around 5,000 traffic camera images from 220 traffic cameras in 22 cities. So we first compare our method with 4 state-of-the-art image registration baselines. We can see that AutoMatch delivers 5 times improvement in image registration accuracy. And we then want to evaluate the accuracy of assisting vehicles localization. So here we show the heat map, which shows the localization arrow across the traffic camera image. We can see that AutoMatch can achieve decimeter level localization accuracy in most of the regions. Okay, so in conclusion, the takeaway is AutoMatch leverages ubiquitous traffic cameras to improve the localization of vehicles without additional deployment. This is achieved by establishing pixel-to-pixel correspondence between traffic camera image and a 2D HD map. AutoMatch achieves precise image registration by extracting and aligning structured key points from ground signs.
Can I ask a question about the evaluation 1 or 2 slides ago? Yeah, that. So the error that you're showing on the y-axis is the pixel, is it the traffic signs on the ground and the errors on the traffic sign? What is the...
Oh, you mean this picture?
No.
This picture?
Yeah.
Oh, the image, okay. So
what is the y-axis?
Okay, the y-axis is the reprojection arrow, which means if we have a ground truth transformation and we register these two images, we can have the pixel-to-pixel correspondence. For example, one pixel corresponds to another pixel in the image, and they are exactly covered to each other. And if we are using our method, there will be arrows, and these two pixels, which should be attached to each other, but there have been some pixels of arrows. Yeah, okay. Yeah.
Did you also measure because as a user, I don't really care about the pixels. What I care is, can I recognize this as an arrow going that way, an arrow going that way? Right? So that's all I care, right? And did you measure that at the higher level instead of the pixel level?
Yeah, for the user's level, I think this picture can give an answer. This picture shows, for example, if a vehicle occurs at any position of the... Okay, first, this picture is a traffic camera image. which is the traffic camera's field of view. And if any vehicle occurs in any of the locations here, and the arrow that the traffic camera can locate it is represented by the colors. Like this color map shows accurately shows the arrows we can localize the vehicles.
Okay. And so from this picture, it looks like near where the arrows are and the crossings are, the accuracy is really good.
Yeah.
4 centimeters, and then when you get farther away from the camera, then you're.
Yeah. That's mainly.
And what's an acceptable? I mean, I don't know what acceptable is because in Brazil, where I come from, 2 centimeters is great because people just. Cars are very close to other. Here, if you have, 100 centimeters, like, oh my God, you're so close.
Okay. I think like a common sense in autonomous driving is that we should have centimeter level localization accuracy for when we are talking about, fully autonomous cars. Yeah.
So this image is after the merge. How did this improve over just the car view or versus just one camera versus?
Oh yeah, and this is not about we want to extend the vehicle's view. It's more about we want to use the traffic camera to localize the vehicles. Yeah. For example, if a vehicle occurs at some place, the infrastructure can send informations to these vehicles to tell them their localization. Yeah.
So, what is your method's advantage over, say, superglue? Is superglue more general? So it's maybe that you have a template?
Yeah. I think the idea why, or the key aspect why our method is better than superglue is more like a general or generic method, and it applies to many image pairs. And if you take a look at their data set, their images are similar in a large extent, I think. Yeah, and if we are looking at the 2 images, and these 2 images, they have very different perspective and the scale. And for superglue, it's hard to accurately find the correspondence. And here we use the prior that in intersection we have ground signs, and we want to extract key points from the ground signs. And this is also our limitation of this work, because we can only do this kind of image registration in intersections, which is not very generic. But I think the key of system work is to leverage the prior of your problem scenario and do some specific designs. I
saw some other hands. If any student wants to, I asked question already. I'll save one for later. Anybody else wants to? All right, I'll ask and then you have more time there. There is an assumption here that the high quality picture from above are fairly recent, so the live picture from the camera matches. It's just an issue of figuring out how to match. But infrastructure in cities, road infrastructure changes. So there are this intersection, for example, they could decide, a bike lane. So instead of 3 lanes, so 2 and 2 arrows, it's like 2 and 1 arrow, for example. So how does it handle when things obviously change?
We didn't consider about this kind of problem, but we can do the HD map updates, in given frequency. For example, we can use the drones to periodically scan the intersection so that we can have the updated ground truth or updated updated HD map. Yeah, and for traffic camera, it as you are seeing, it is live, and we can just capture the images and match it with the updated HD map. Yeah, maybe we can do this kind of algorithms periodically. I think. Yeah.
I mean, one idea here could be you could see one live to the next live. If, you can even tell, oh, there's crew changing the lines, right? So there is, comparing the differences. And another idea could be intersections oftentimes don't have camera on the one side only. There could be 4 cameras. So maybe there's something, if you pull those images together, that might be another paper, I don't know. But that's another, because you saw the map that Daniel was asking earlier, the error map, clearly was better when it was the camera, closer to the camera.
Yeah.
And the farther away you got, it was worse. But if you superimpose from 4 different angles, 4 different directions, those cameras, then the error completely goes away to some degree, right? So, that would be an idea.
Yeah, and actually we have the third work is about how to detect the changes in the rows. Yeah, maybe we can wait. Yeah.
Cool. What's the false positive rate on the image detection?
False positive rate? Oh, maybe we can. I don't show the results here, but in our paper we have detailed evaluation. But for the specific number, I cannot remember it.
Like if I were to go to some random road and make it take some sticks and make it kind of look like a ground side, will it say that's a ground side, or will it recognize it as a pile of sticks someone did?
Oh, I'm sorry.
So how often does it misrecognize random objects or paintings on the ground as the ground side?
We have such kind of evaluation in our paper, but here I do not include it in my slides. Maybe you can check our paper, but for the specific number, I cannot clearly remember it.
One question. So is there a reason you're using only the camera and not something like a GPS on the drone to help map the world to the camera, which could help with changing lanes and all of that? Or is just an assumption and you're right?
For the drone part, the drone do have GPS or even higher quality localization devices on it, so that it can produce such kind of accurate HD map. And for this paper, we just want to leverage the existing traffic cameras as it is, which means if they do not have a GPS on the traffic camera, we just accept it and do the research.
But traffic cameras don't move, right? So they always have GPS.
The key here is the traffic cameras are randomly installed, right? And we don't know the exact location and direction of these traffic cameras. And if we already know the information, actually the localization is already done.
Otherwise, there would be a lot of intersections look the same.
But
if you were just to compare with random
only
intersections
use
everywhere.
the fixed cameras, yes. But in this example, we have the moving flying vehicles, if you have cars, and those are movable, right? But they still have more sensors. That I'm guilty of this. Let's make the worst case for myself and try to solve it.
One limitation is our data set is from a company from China, and we do not have the right to control their drones. We only get the HD maps. So
another maybe related to the question is that all these images are under perfect conditions. So the weather, if it's snow or whatever, that might obstruct or give different or shadows. This approach will fail.
Yeah. Okay. The key.
Trees, all these kind of things.
Yeah, one property of the traffic camera is that it is fixed, right? As I mentioned before, maybe we can have the like this kind of idle scenario and capture these kind of images to do the registration, because the registration is a one-time work or one-time thing, and once you get such kind of registration or such kind of localization map, you already can localize the vehicles inside the traffic camera's view. Yeah, it's more about an offline work. Yeah.
So no place on earth is so terrible all the time is the answer. There would be some nice things. Some maybe not as many, but.
Yeah. Okay. So previous two works focus on the sensor data registration or the sensor data fusion between infrastructure and vehicle. So in the third work, we want to take one step further to explore the potential of using infrastructure to assist vehicles' scene understanding. Scene understanding is very different from perception. It involves not just detecting or recognizing objects, but also understanding the layout of the environment, so that we can have an idea of the potential interactions between the objects. So if we are talking about the vehicle's scene understanding, an essential component is the HD map. So in this work, we want to explore the opportunity of utilizing infrastructure to do the HD map construction. First, let's try to understand why HD map is important. It helps autonomous vehicles to accurately localize themselves, figure out what the world around them looks like, and do context-aware decisions. And it is reported that the global market for HD maps is growing drastically, and it will be worth about $17 billion by 2030. So what's HD map? It comprises two components: the geometry part and the topology part. For the geometry information, it provides precise locations and the semantics of the map elements, like lanes, road boundaries, lane dividers, and crosswalks. And for the topology information, it describes the connectivity of lanes, illustrating how these lanes are interconnected. So basically, there are two major ways of building HD maps, either offline or online. The offline approach first performs data collection, for example, by using a high-end survey fleet to scan the roads many times. Then the data collected is annotated manually for building a globally consistent map. This approach leads to comprehensive maps. However, due to the extremely high cost, its update frequency is low. So to address the challenges faced by the offline scheme, a new scheme is to estimate the local HD map on the fly, only relying on the onboard sensor observations, such as the LiDAR point clouds or images of the vehicle to do the HD map construction. So this kind of online approach, it generates the most up-to-date HD maps, but it also makes HD mapping more scalable. However, many dynamic factors, such as the blockage of the vehicle's view, can make the online maps inaccurate and fragmented. So in this work, we propose a completely different mapping scheme by leveraging the roadside infrastructure for HD map construction. And our work is motivated by the following two key observations. The first observation is that the infrastructure can continuously observe the road section at a standstill and accumulate points. Yeah, this video shows how infrastructure's point cloud accumulates over time. As you can see here, with the accumulation, it brings comprehensive, unblocked, and high-quality sensor data, which makes up for the shortcomings of vehicles' online mapping. Besides capturing the road information, our second observation is that infrastructure can detect and track vehicles using its LiDAR, and such kind of trajectory is highly precise because the LiDAR itself has highly accurate range detection. So these precise trajectories can help us to determine the map geometry and topology. For example, the trajectory direction can reflect the map topology, indicating the directed connectivity between lanes. And the trajectory density, it separates the lanes and helps us to find the lane dividers and road boundaries. So in summary, infrastructure can offer information of both map geometry and topology, which are the two essential components of an HD map. So based on these observations, we designed our approach VI-Map. VI-Map is the first system to leverage roadside infrastructure for real-time HD map construction. Here is the processing pipeline of VI-Map. First, the infrastructure uses the accumulated point cloud and the precise trajectories to construct map geometry and map topology, respectively. Then the infrastructure transmits the HD map to the vehicle. And for the vehicle side, the vehicle receives the HD map transmitted by the infrastructure and fills it with its own HD map. So next I will introduce each module separately. So for the geometry construction part, recall that we have the accumulated point clouds and also the accumulated precise trajectories, and they both contain valuable information of map geometry. So we want to use these two kind of inputs to do the geometry construction. However, these two kinds of information, they are massive and unstructured and also heterogeneous. So our challenge is that how can we efficiently process such massive data in real time? Our idea is to project such data into the bird's eye view and extract very lightweight features tailored for generating the map geometry. And the geometry information alone is not sufficient. We also need the topology information, which describes the connectivity between lanes. Estimating such connectivity is actually straightforward for the infrastructure. So if two lanes are crossed by the same trajectory, they are considered to be connected. So in the map, all the connectivities are actually directed, which can be calculated by the direction of the trajectory. So based on this intuition, we use a directed graph to represent the topology. The graph's nose corresponds to lanes and the edges corresponds to the connections between the lanes. And a nice property here is that as more and more trajectories are observed, we gradually obtain the complete map topology. Now we have the map geometry and the topology, which forms a complete infrastructure HD map. And the infrastructure HD map is ready to be transmitted to the vehicle. After the vehicle receives the map, it merges the infrastructure map with its own HD map. To merge the two HD maps, we first leverage the semantic attributes and the spatial proximity to find the corresponding map elements. Then by refitting each pair of corresponding map elements into a unified representation, we can get a merged HD map. We evaluate our system on both a real-world testbed and the color simulator. The real-world dataset is collected from 18 road sections in 2 cities, covering a variety of road types such as T-junctions, crossroads, and street roads with different lane numbers. In total, we collect around 14 gigabytes of data from the real world and the simulator. This table shows the accuracy of the generated HD map. We can see that VI map surpasses vehicle's online mapping baseline, which is the HD map night baseline. It greatly enhances the on-vehicle HD map. In general, VI map can provide vehicles with decimeter level HD maps. We also evaluate the latency of each step of map fusion at different road types, and the results show that even at the complex crossroads, the overlay delay is less than 50 milliseconds. This shows that VI map can support the real-time map fusion between the infrastructure and vehicle. So here we use a demo to show the comparison between the online HD map construction methods and VI map.
We will show a video of a vehicle passing an intersection to compare the online HD map built by the vehicle using onboard sensors and our system, VI map.
Here shows the HD map generated by online methods. We can see that the online methods, they are sensitive to occurrence, which will result in incomplete HD maps. Here, the vehicle receives the infrastructure's HD map and fills it with its on-vehicle HD map.
Do you also have what the infrastructure map would be? Just infrastructure.
Okay, the just infrastructure is like in the middle of the...
We will show a video
I'm sorry. In the middle of the... Yeah, it will be like the top part of the map.
The intersection from the infrastructure.
I think so, yeah.
Yeah, we can see that with the help of the infrastructure, the vehicle can...
VI map boosts on vehicle HD maps by providing additional accurate road geometry and topology.
Okay, so in summary, the takeaway is VI map leverage the stationary cumulative observations from roadside infrastructure, such as the accumulated point cloud and the precise vehicle trajectories to construct accurate, up-to-date, and scalable HD maps for autonomous driving. So, in conclusion, we developed 3 techniques of leveraging infrastructure for assisting autonomous driving. And in VII, we propose to use LiDAR on infrastructure to enhance vehicles' 3D perception. And in AutoMatch, we focus on widely available cameras to assist the localization of vehicles. And finally, VI map leverage the unique features of the infrastructure to provide vehicles with the fresh HD map. So at the end of the talk, I would like to thank all of my advisors for their guidance on my research, and all of my collaborators for their valuable contributions that have enriched my work, and all of my mentees that for their trust. So with this, I conclude my talk, and thank you for listening. Now I'm happy to take questions.
All right, questions?
More questions during the talk, but if there are some now.
Yeah, we may.
So I have one sort of overall question, especially with the first and the third, where you're definitely getting these better understandings of the world around you, but because, or in my mind, like the autonomous vehicles, they only have so much compute, right? So the amount of compute you're spending on getting this better understanding of the world, is that taking away or like increasing the latency between like you and your ability to make a decision on that world, if that makes sense?
Yeah, I want to mention that actually we are not adding latency to the autonomous driving pipeline. For example, for the first work, we only as like inputs for the vehicles, and the vehicles autonomous driving pipeline is the latency is fixed, right? And we only enhance the inputs or the sensor data of the autonomous vehicles. And for the third work, actually we are fusing the maps at the result level. Yeah, which means the vehicle can choose to, after the, one intuitive example is after the vehicle can choose to merge the two HD maps, and after it has done this kind of registration, it can benefit its following driving or its following operation.
So it's sort of buffered enough where like you're getting this information far enough in the future where like the processing run doesn't really affect the time we're actually going to be using that information to make a decision.
Oh, okay. Yeah, we do need some like computation to do this kind of like fusion or registration, and you can view it as like a sideline of the processing, right? And once you have this additional information, you can merge it into your own pipeline. Yeah, and I think this kind of merge time is very limited. Yeah.
So quick question is like, so when you communicate with the station, the communication overhead will, so the information I get from the station is stable, right? Compared to the one I get just from my own sensor. So how do you deal with this? For example, like there's a car in front of me.
Yeah.
When he gets,
The key is we can give the rough idea of the vehicle what it is missing, right? And if the vehicle can get the information from the infrastructure, it can do some like compensation itself. For example, if we have this delta T delta T, already passed, and the vehicle can predict for example, the other vehicle's motion based on the infrastructure's information. And within this very short time of delta T, I think the prediction should be accurate enough for the vehicle. It's the key idea is the vehicle can know 0 or 1 information, right? Whether there is other vehicles or pedestrians, it is the most important. And and about the accurate location or the accurate motion of these vehicles or pedestrians, I think in such short of time the vehicle can do its own prediction. Yeah.
I have a question. So, in your paper, so the position of vehicles can be read by X, right? Is it a point or is it a one box? It's a coordinate. You can view it as X, Y, Z. Yeah. So usually when we say vehicles, we see that SUV, sedan, or some small vehicle. But for truck with a cargo, the shape of vehicle is changing when they just turn left and turn right. Usually this kind of vehicles. Because if you drive a truck with a cargo, and the vehicle maybe follow the path on your map, but the cargo is rotating in a straight or where path. How do you?
I think the cargo can be taken as another car as well.
As another car.
So that confound the algorithm? Will the algorithm think there are 2 objects?
It depends on the recognition algorithm, right? But basically, you can. The symbol is taken as 2 separate cars and follow the same pattern, right?
Okay.
Right. I think,
Just follow up on this and then my second question is, in the case of cargo, the curvature of I think that what's he trying to say, the curvature of the path would be different for the cargo and the vehicle. 2 vehicles will follow a different curvature versus a truck and a cargo that's following behind it. And that's why they have to take longer while it turns. And that's the other thing said that. So that's something that would have to be considered in the algorithm.
I think it won't be affected by, like, it would not matter for the algorithm.
As we are like accumulating these trajectories, right? And there may be outliers at the side, but the majority of the trajectories, it should follow the correct trajectory or correct rule,
And that changes in that pattern could even be used to address that issue where the road changes, I guess.
The key for the third work is we can actually do such online HD map construction, which means when there is like changes in the, for example, in the road topology. For example, one car has an accident and it blocks several lanes, but not all lanes. And using our approach, we can update the HD map very quickly, so we can know which lanes are blocked and which lanes are not blocked, and which is a great benefit compared to other like HD mapping methods. For example, the offline HD mapping methods, it is more comprehensive, but it cannot reflect on these kind of changes very quickly.
Go ahead.
You mentioned that the car has the ability to choose to merge the data that's retrieved from the infrastructure. Could you sort of build upon what is the criterion based on which it chooses, so that how does it determine whether the data input that's coming from the infrastructure is good enough to be merged, or versus it's corrupted, or something totally different?
We have some follow-up projects on this kind of questions, which is the reliability of the infrastructure output, and how can the vehicle do the choice or to predict whether the data is good or not. This definitely a new kind of research problem.
All right, I may have another final question. So, how do you think about the future autonomous driving? Like, there's a bunch of work on trying to fuse many different sensor data, right? Like you have MU, you have like LiDAR, you have like cameras, and so forth. But Tesla is pushing a lot on single camera based solutions. Which do you believe is the future? And like
I think our ultimate goal is fully autonomous driving, and as you said, there are different like paradigms of autonomous driving, and we also have other paradigms. For example, like what I shared, the infrastructure assisted, and also we have like connected vehicle autonomous driving. I think I'm not great enough to choose which paradigm is greater than the other one, but I think my research, the goal of my research is to explore the potential of this kind of paradigm and see whether it can provide insights to the industry.
All right, with that, I need to speak. Thank you.